For 6 intense weeks during the summer of 2013, 37 pre-freshman students from Morehouse, Clark Atlanta University, and a local high school participated in the HARP program. Nothing has such power to broaden the mind as the ability to investigate systematically and truly all that comes under thy observation in life.
My name is Dr. Lycurgus Muldrow. I'm the Director of Sponsored Research and Integrative Activities for the Division of Science and Mathematics at Morehouse College. HARP stands for High Altitude Research Project. It's a term that was developed by a number of institutions that have created a team of undergraduate schools, mostly in engineering, learning how to do high altitude research balloon launching. We have a program called the Pre-Freshman Bridge Summer Science Program. And this pre-freshman Bridge Summer Science Program is for pre-freshmen that are interested in going to college at Spelman, Clark Atlanta University, but specifically at Morehouse College. So we can take this and incorporate this into our summer program where the students actually send research projects to the edge of space and back and recover them. And I'm always looking for exciting new projects in this pre-freshman Bridge Summer Science Program that will inspire the students to go to the next level. And when that opportunity came, I knew we had to do it.
Welcome to the laboratory component, the HARP, which stands for High Altitude
On June
Research.
10, 2013, the Morehouse STEM program commenced for the 7th year. 37 pre-freshman students from Morehouse, Clark Atlanta University, and a local high school
number one,
began
two,
their
or
HARP
three
experience.
lab that you like to go into, and then we're going to match you up based on your number one preference, number two preference, or three preference, and your major. For example, if you're majoring in mechanical engineering, it makes sense that you should, for example, be on the launch recovery and design team that's designing the craft. Or if you're majoring in computer sciences, it may make sense for you to be in one of the robotics teams that has to program these robots to do specific things in this launch, okay?
So these are the 5 basic groups of research that's going to be involved. However, none of this can take place unless we have a balloon launch. And so we've got a design, launch, and recovery team, but we also have responsibility for designing the payload and then tracking that balloon as it launches and then doing the recovery. Besides mentoring this group, I also act as sort of a coordinator for the other research groups so we can bring all of the research experiments together to go onto the payload that's launched into the atmosphere.
My name is Dr. Juana Mendenhall. I am an assistant professor at Morehouse College in the Department of Chemistry, and I'm with the biomaterials team. Can mean like biological, right? Something like of the body, or something that can be biocompatible for the body so it won't kill anybody, right? And a material is simply something that can be man-made, something that's synthetic. We can actually make it in the lab. What we do in the biomaterials lab is that we actually fabricate biomaterials that can be used as scaffolds or tissue scaffolds in someone's body. So the use of actually taking our materials up in a weather balloon will allow us to see what would happen to materials if they were implanted in someone's body. So what the students have actually done in our lab is actually started implementing therapeutic agents into the materials to see if they can actually help control degradation process and hopefully have a healthy effect on tissue regenerating at higher altitudes. The HARP balloon is going what? It's going constantly up in the atmosphere. As it goes up, it's depleting out the oxygen levels that are essentially down here on Earth, right? So as it starts going up, we want to study how that depleted oxygen level, or that level of oxygen, actually affects our materials. Now, if we can figure out how materials are affected at that high altitude, we can do what? We can alter it using some chemistry, change the materials we make to make them more optimal, so as they go up in the altitude, that they will actually capture those unwanted molecules that are in the air, and they'll essentially heal somebody's body if they're going up in space or if they have a disease state in their body. Okay?
What we're doing this summer is working with this program to help some of you learn how to shoot video, how to edit video. You'll also be documenting your fellow HARP student participants as they go about developing their aspects and components of this project.
So my name is Darkale Reuben. I'm a postdoc at Clark Atlanta University in the physics department, and I am a facilitator for the battery team, so a lithium-air battery team.
I'm Dwayne Jackson, professor of psychology now. I am the team leader for the termites who are going up in space, which we're very excited about.
I'm Mihiru Shashikala Hewa Bostantirige.
I'm Indra Sapkota. We are energy group, so we have to generate energy from sustainable source. So.
I'm Ms. Thomas. I will be doing the robotics class. I am a PhD candidate at CAU in computer science, system science / computer science.
The robotics aid the biomaterials lab by constructing a mechanical arm that opens up the petri dish at a certain altitude and have it open for a certain time frame and then close it. Also the robotics aid the graphene lab where we have 3 different valves that they have materials in, and the robot was created to rotate between those 3 different valves, opening them up at certain time intervals and then close them.
Now the students get out of working with me really how to be a scientist. They learn how you deal with proposing a question or a purpose, forming a hypothesis, and then actually doing the research, knowing that you're going to have a lot of blind alleys and you're going to have more failures than success.
They come up with the design themselves, they come up with the programming, and so this is really a hands-on guided inquiry lab where the students take charge and they develop their robots on their own.
And these are students that have declared a STEM major. STEM stands for Science, Technology, Engineering, and Mathematics. We've been doing the program, this is our 7th year. And the emphasis on this program is scientific literacy. The idea is real simple. 17% of the United States population is not scientifically literate. They don't understand how research happens. They don't understand how science happens. And because of that, they really have a disconnect between science. The reality of it is incoming freshmen that say they want to major in science are not scientifically literate. So if we could show them the big picture of science, have them do a little research, have them do a little science, the literature shows that they may become more excited about science and then stay in science. And it's a dismal national outlook on science and STEM simply because 40% of African American students that start a major in STEM don't finish it. So this pre-freshman bridge summer science program, which we've been doing for 7 years and tracking the data, has shown that the students do much, much better in their courses and they stay in the major. In fact, 15 to 20% better than the average other STEM students that didn't participate in the summer program.
The Recover team was composed of 6 students, given the responsibility of mastering the Stratostar kit, which included learning how to launch the balloon and recover the craft containing the research payloads. This team was also responsible for designing the payload craft that would carry the 5 research projects into near-space conditions. The payload craft was creatively designed with specific size specifications with a specific weight load requirement under 12 pounds.
Our little container, that's our balloon launch system.
We do what is called an engineering design process, where we are trying to realize what the problems are from the other research groups and how we can accommodate them and get all of their research programs situated in a containment vessel that will go up with the balloon, and it has to be able to survive coming down with a parachute. So it's not going to be a gentle ride coming down, so we've got to design for that.
My name is Dakari Franklin, and I'm with the design and launch team. This is the pool noodle. It was longer like a regular pool noodle, and we've been cutting this and using this as the cushion for the fall.
And then the students get to build this payload section. The other thing is that they have to learn how to use a GPS device to track. They have to learn how to read a regulation, a federal regulation that governs the launch of these balloons.
What this does is it transmits to the command module, which is now outside, and we're trying to get it to, it's actually sending back a signal to me over here on the antenna. But what it doesn't send me yet is the GPS coordinates. It takes a while for it to pick up GPS coordinates. Every time it moves somewhere, it then has to figure out all the various satellites. essentially built in to receive from the satellite. And GPS satellites never receive data from it. They just send data out, and you capture it on your device and then use it.
How much do you?
They have to learn how to deal with simple mathematics to predict where that balloon might go with the winds that are prevailing that day. You got 33 degrees, and that's in degrees. Okay.
33 divided, take 7, 4, 8, 9, 7.
No, you got 0.7, isn't it? We're trying to launch a flight that doesn't require us to get permission from the federal government. So we have to fall within certain limitations. And the first limitation is can't weigh over 12 pounds. You can't obviously launch in a airspace, controlled airspace, such as around an airport. You can't launch if over 50% of the cloud cover. And you have to have a visibility of 5 miles. The problem that we have really to deal with is the weight restriction. The weight restriction requires a limit of 12 pounds, not counting the balloon, but everything else, the parachute, the instrumentation, and all of the experiments that the students produce, all has to fall into that 12. Guys, there is something going on. I don't know what. Neither one of them is working, so we do have a problem. Be careful about pulling on the antenna. It might be better to push. Yeah. Go ahead and take that.
You always need a light skin in the picture.
Because we interact with all of the other teams, the research teams, we have to become aware of what their requirements are and what the purpose of their research is, so we can design our module to accommodate their needs. So my team has a liaison for each of the other research teams. But what I want them to do is to hook it up with their solar cells and see if it heats up.
Well, what they said they were going to do is their solar cells are recharging a battery, and they'd hook this up to that battery.
My name is Caleb Bugg, and I'm part of the Sustainable Energy team here doing the HARP project at HBCU Up Camp. Right now, we're trying to maximize the use of our solar panel. So currently we're doing outdoor testing, of course trying to get the maximum amount of energy from the sun. We've Googled that this is a 1 watt resistor, and we're not quite getting that on our readings yet. So we've come up with a couple ideas, such as using tinfoil.
My name is Matthew Mullins. I'm here with Sustainable Energy. And right now we're trying to see if this aluminum foil can help increase the sun's intensity on our solar panel.
Our mentors are teaching us about resistance and things like that, and how voltage and resistance and all these electrical engineering tools combine to make like watts increase, or like the relationships between all of these. So right now we're just finishing up our outdoor test, and we're going to have a lot more tests during the week and during the following weeks, and we just hope that eventually we'll be able to have a foundation for the kids that come after us in this program, so that we can eventually have a sustainable energy source to replace the batteries that are being thrown out every year. The reading now is at about 0.5 watts, and that's at about 2.3 volts. So as I mentioned, it's a 1 watt solar panel, so we want to get it from 0.5 to as close to 1 as possible. The chances that we can get 100% efficiency aren't very high, but to think that we can get into the 0.8 or 0.9 range is very likely. So that's what we're trying to do. So you have to use, like I said, the electrical engineering tools. We're using small resistors, we're using increased sunlight intensity, things like that, and we're trying to maximize the wattage. Wattage is joules per second, so wattage is telling you like your power output in a given amount of time, and that's what you want to increase in order to power something such as the HARP payload.
So the objective of the battery team is for the students to work together, first learn what a battery is, the history of batteries, and what is the latest technology in battery technology. We got our prototype batteries from Acceleratron, a local Atlanta company.
Did we get everybody fitted in all right? I thought maybe we might not have enough chairs. Yeah. So everybody came that you had planned to come? Yeah. But let me first introduce myself. I'm Tony Pace. I'm the Chief Operating Officer for the company here. I'm glad you guys were able to come visit us today. Appreciate you coming by to listen to us and see what we're talking about. During the course of the day today, I'll ask you some questions. We'll talk a little bit about what we're doing here, and hopefully I'll get a chance to find out some of what you guys are doing, and I'll give you a short tour, and then once we're back from the tour, then you'll be able to talk to Dr. Johnson. You can ask him some questions as well about him and his background. So
there was a man named Lonnie Johnson who has become the idol and an icon for current black scientists today. He was an engineer at, I believe it was NASA, where he worked on some of the space shuttles, and he invented the super soaker water gun, and a lot of people know him for that.
Some of the work that we're doing here is very secret work, and most of it is proprietary. So we're cautious about what ends up on film because we don't want our competitors to find out, what we're doing. And so you guys will have to bear with me during the course of the discussions today, particularly the cameraman.
Later, he started his own firm called Acceleratron, and a couple other engineering firms. A long time ago, we sort of got in touch with him because he's in the Atlanta area, and we developed a relationship with him. So every summer, we send students to Acceleratron to do research. We wanted to expand that relationship, and when we knew he developed this air lithium battery, we asked, well, and they have a contract to put one in a blimp, but it's not been sent up to the edge of space. A blimp that goes up and stays for a year. So what happened, we said, well, can we send one of the batteries up, just to test to see how it works, which is a great research project.
The original question is, what's so special about this lithium air battery? Okay, and sorry?
High energy.
Somebody said it has high energy. The question is how much higher energy does it have, right? Okay. It took the guys at NASA, what was it they said, 10 years to get a 10% improvement on lithium ion batteries, all right? The battery technology that we're working on here has the potential for 10 times the energy of conventional lithium ion batteries. So if you're driving this Toyota Prius, right, and you replace that Toyota Prius battery with our battery, you should be able to go 600 miles on a charge, right? If it's 10 times, yeah? Come in and say that louder so everybody can hear you.
He was creating a heat pump that used water instead of Freon, and he ended up aiming one of the hoses at a tub and it shot water.
So that's how you came up with the idea for the super.
Yeah.
Very good. Okay. One day while Dr. Johnson's in class, there's a professor talking about thermodynamics, right? That particular day he was awake and listening during class and got the idea for the super soaker, okay? So for all the rest of you guys, you have to be careful. You don't want to be asleep in class because a $2 billion idea just might go straight over your head, right?
Welcome to Atlanta, for those of you who have come from afar. Let's see, I guess Tony's probably told you a lot about what we're doing here in terms of the energy technology development. Progress has been made with some of the corrosive issues with lithium air batteries. There are two types of corrosive issues. There's the bad kind and the good kind. Batteries work, the lithium air battery that Tony I'm sure talk to you about, that discharge process is a corrosive process. The lithium is coming over into the air and getting oxidized, and in the process you generate electricity. The bad corrosive type is when you have a defect in the packaging and air or oxygen can get into the battery and react with the lithium without having it discharge or something like that.